Welcome to MarkScheme. Sum to infinity. Everything you need made visual. Here's a 2,000-year-old puzzle. To cross a room, first you have to cross half of it. Then half of what's left. Then half of that. Then half again. There are infinitely many of these steps. So how could you ever arrive? This is Zeno's paradox. Add up those steps. 1/2 plus 1/4 plus 1/8 plus 1/16, on and on forever. Infinitely many positive numbers. Common sense says an endless sum should blow up to infinity. And yet you do cross the room. By the end of this video, you'll see exactly why this infinite sum is finite. And you'll have a one-line formula for it. Here's exactly what this covers, straight from your syllabus. IB analysis and approaches. Standard level 1.8. The sum to infinity of a geometric series, u1 over 1 minus r. The condition it needs, that the absolute value of r is less than 1. Why that condition is forced on us. And the exam craft, spotting hidden geometric series. This sits right on top of geometric series from 1.3. If you haven't seen that video, watch it first. Here we simply take its limit. Let's actually build that sum. Here is one whole bar, length exactly 1. Our first step covers half of it. Now each new step covers half of the gap that's left. A quarter, then an eighth, then a 16th. Watch the running total, 1/2, then 3/4, then 7/8, then 15/16. Every block is half the one before, so each one is smaller, and the total keeps creeping toward the far edge. But look, it never crosses the green line. It never overshoots 1. Each step closes exactly half the remaining gap, so there's always a tiny sliver left, and that sliver halves every time. The gap shrinks to nothing. The infinite sum equals 1, finite and exact. Compare that with a geometric series, where the ratio is 2, so each term is double the last. 1, 2, 4, 8, 16. Now the blocks don't shrink, they grow. Each step adds more than the one before, so the total races off to infinity. There is no sum to infinity here. It diverges. The whole idea only works when the terms die away. And that is the condition we're about to pin down. Time to derive the formula properly. We already have the sum of the first n terms of a geometric series from the previous video. Sn equals u1 times 1 minus r to the n, all over 1 minus r. The sum to infinity is just what this settles down to as n runs off to infinity. Everything hinges on one piece, r to the n. Suppose the absolute value of r is less than 1. Say r is 0.5. Then r squared is 0.25. r cubed is 0.125. And it keeps shrinking. Raise a number smaller than 1 to higher and higher powers, and it collapses towards 0. So as n goes to infinity, r to the n goes to 0. Now set r to the n to 0 in the formula. The bracket, 1 minus r to the n, becomes simply 1 minus 0, which is 1. And the whole sum collapses to u1 over 1 minus r. That's it. The sum to infinity. No new trick, just the limit of a formula you already know. Before we use the formula, here's a second derivation, shorter and genuinely beautiful. Write the whole infinite sum out. Now factor r out of every term after the first. What's left inside the bracket is u1 plus u1r plus u1r squared, and so on, which is exactly the sum we started with. The infinite series contains a perfect copy of itself. So S equals U1 plus R times that S. Now it's just algebra. Bring the RS across, factor out S, and divide. S equals U1 over 1 minus R. The very same formula, with no limits at all. And notice, this self-similar trick only closes up if the tail is smaller than the whole, which is precisely why we need the size of R below 1. But that derivation only worked because R to the n died away. And that needs one thing: the absolute value of R strictly less than 1. This little inequality is the whole ball game. So let's see what happens on either side of it. If the absolute value of R is less than 1, R to the n heads to 0. The series converges, and the sum exists. But if R is bigger than 1 in size, R to the n blows up. It diverges. No sum. If R equals 1, you're just adding U1 to itself forever. And notice 1 minus R is 0. So the formula would divide by 0, a dead giveaway. And if R is minus 1, the terms flip, plus, minus, plus, minus. So the total never settles. Only the first line survives. The absolute value of R less than 1. That's the condition. Here's a question examiners love. For which values of x does a series converge? Take 1 plus x, squared plus x cubed, and so on. That's geometric. First term 1, and the common ratio is simply x itself. So the convergence condition, the absolute value of R less than 1, becomes simply the absolute value of x less than 1. That is, x strictly between minus 1 and 1. Inside that green band, the sum exists. Step outside it, and the series diverges. And when it does converge, the formula gives a lovely result. 1 over 1 minus x. Whenever a ratio carries a variable, just solve the size of R below 1. Let's build a ladder of examples. Easy to hard. All my own numbers, IB style. Part 1. Forwards. A geometric series has first term 12 and ratio 1/3. Find the sum to infinity. Step 1. Always. Check convergence. The absolute value of 1/3 is less than 1. Good. It converges. And that check is worth a mark. Now substitute into U1 over 1 minus R. 12 over 1 minus 1/3. 1 minus 1/3 is 2/3. And dividing by 2/3 means multiplying by 3 over 2. 12 times 3 over 2 is 18. Part 2 runs it backwards. A real favorite of examiners. An infinite geometric series has sum to infinity 20 and first term 15. Find the common ratio. Set the formula equal to 20. 15 over 1 minus R equals 20. Multiply up. 15 equals 20 times 1 minus R. Divide by 20. 1 minus R is 15 over 20, which is 3/4. So R is 1 minus 3/4, 1/4, and a quick sanity check. The absolute value of a quarter is less than 1. So this series really does have a sum to infinity. Answer: R equals 1/4. Part 3. And this is where the sum to infinity earns its keep. Write the recurring decimal 0.1818, repeating as an exact fraction. The trick is to see it as a sum. 0.18 plus 0.0018 plus 0.0018, and so on. That's a hidden geometric series. First term 0.18, and each term is 100th of the one before. So r is 0.01, comfortably less than 1. Sum to infinity, 0.18 over 1 minus 0.01, which is 0.18 over 0.99. Multiply top and bottom by 100 to get 18 over 99. And that cancels to 2 over 11. A repeating decimal pinned to an exact fraction. Part 4, the trickiest and the classic. A ball is dropped from 10 meters, and each bounce reaches 60% of the height before. Find the total distance it travels. The catch is the geometry. The first drop happens once, but every bounce is traveled twice. Up, then down. So account for it in pieces. The initial drop is 10 meters, counted once. Then the bounce heights, 6, then 3.6, then 2.16, form a geometric series, with first term 6 and ratio 0.6. Because each of those heights is climbed and then fallen, we take twice their sum, to infinity. 2 times 6 over 1 minus 0.6. 6 over 0. 0.4 is 15. Doubled is 30. Add the original 10-meter drop, and the ball travels 40 meters in total before it comes to rest. The whole distance of an endless bounce, a finite 40 meters. Now the exam craft, other channels skip. The biggest one, recognizing a hidden geometric series. A recurring decimal is secretly 1. 0.4 recurring is 0.4 plus 0.04, and so on. First term 0.4, ratio 0.1. Sum to infinity gives 4/9. 4 quick rules to bank. 1. Spot hidden GPs, recurring decimals, and bouncing balls. 2. For a bouncing ball total distance, it's the first drop once, plus twice the sum of the bounce heights. The up and down doubles everything after the drop. 3. Always write the absolute value of r less than 1 check. It's a mark on its own. And 4. On paper 1, leave your answer exact. And when a ratio hides a variable, just solve the size of r below 1. Finally, the 4 traps. 1. Firing off u1 over 1 minus r when the absolute value of r is 1 or more. There simply is no finite sum, so always check first. 2. The sign slip in 1 minus r. If r is minus 0.5, 1 minus 0.5 is 1.5, not 0.5. Subtracting a negative adds. 3. Confusing S infinity, the sum of all the terms, with Sn, the sum of just the first n. And 4. In a bouncing ball problem, forgetting that the first drop counts once, but every bounce counts twice. Dodge these, and sum to infinity is free marks. And that's SL 1.8, fully covered. The sum to infinity, u1 over 1 minus r. Why it only works when the absolute value of r is less than 1. Both ways to derive it. And everything from recurring decimals to bouncing balls. Next in the course, we point geometric growth at money, compound interest, and depreciation. For more, that's MarkScheme.app. See you there.